So far we have been discussing about noise, thermal noise or white Gaussian thermal noise, white Gaussian noise, all are the same. We saw how to go about analyzing them, right? So we saw a couple of examples also. And the important thing that came out from the discussion was the fact that, let's say you put together your circuit and you find that your noise is larger than what you wanted it to be. When I say noise, inherently you should assume that I'm talking about signal to noise ratio. If I just say noise, I'll assume that the signal is not changing and I'm only talking about noise, right? So that's the generic way of dealing with noise, because it's clunky to say signal to noise ratio every time or SNR every time. So if I just say reduction of noise, keep at the back of your mind, imagine that the signal power is not changing, right? So if the signal power is changing, then you have to go back and calculate SNR. So we saw if you have to reduce noise, then the easy way to do that is to take the identical copy of the circuit, connect them node to node in parallel. So you'll see that effectively the SNR will double at the expense of power consumption. And if you want to reduce it by n times, or rather increase SNR by n times, then you put n of the circuits in parallel. N times power consumption, your SNR will also go up by factor of n. In dB, that means 10 log n, right? Because you're talking about power, it's like 10 log n. So naturally, what is 10 log 2?
6.
No, 20 log 2 is 6. 10 log 2 is 3 dB, right? So generally, you are going to hear a lot of things when you read papers that we get 3 dB improvement in SNR by burning twice the amount of power. That essentially means this, right? So you double the power, put things in parallel node to node, you get twice the improvement in SNR. In dB terms, it means 3 dB improvement, right? Okay, fine. So in today's lecture, so let's yes.
Distribution is increasing. So
Yes.
we cannot do anything for power be less in SNR.
So this is the method that I am alluding to right now. It's universal way of increasing SNR, right? So you do not have to be a genius to do this. You just take the circuit, take another copy, slap, and then done. But later you'll see that. Okay, why later? I can even talk about it now. So let's say you are not talking about a single block. A system will obviously have 3-4 blocks or many more blocks. One of the blocks might have more noise contribution than the others, right? So let's say I say that one block has, just take numbers. Let's say one block is consuming or rather contributing 10x the noise of all the other blocks combined, right? And let's say this block is consuming equal amount of power with respect to all the others, right? So basically what I'm saying is, let's say you have a network where you have something like this, and you did the noise analysis and you found out that maybe this one is consuming P amount of power and all of these are consuming P amount of power together. And let's say for some reason this is a different network, maybe this has a noise power spectral density of 10 nanovolt per square, or not necessarily nanovolt right now. Let's say 10 into 10 power minus 18 volt square per hertz. Okay, and these all of them combined has, let's say 5 into 10 power minus 18 volt square per hertz. So don't get scared of these numbers. These are typical numbers that you tend to get in analog circuits. Once you start doing the assignments, you'll be get used to these numbers. So now let's say I want to reduce the power. No, I want to increase the SNR by a factor of 2. Then all I need to do is copy the entire thing again and connect node to node, right? So SNR will go by factor of 2. Power consumption will also go by factor of 2. But if I am smart enough, then I will probably see that this guy is a major noise contributor. If I reduce this by maybe a factor of 2, then probably I will get a significant reduction in the overall noise while not doubling the power, right? So maybe I decide to put this in parallel and the others I let it be. Right? So that way you do not get like twice the amount of power, and you get some amount of SNR improvement, right? So type of things are even more prominent if, let's say, these subsequent blocks was consuming 10x the power, let's say, right? So then naturally increasing this power in the quest for reducing noise makes more sense, because in any way this is consuming only 1/10 of the total power or 1/11 of the total power. If I increase this by 2x, the total power only increases by 10%, correct? But this guy goes down from 10 to 5. Right, so lot of improvement in terms of overall system SNR without doubling the total SNR of the total power of the system, right? So that's why when you are doing any analysis, you'll have to figure out which block or which transistor, for example, or which block is a dominant noise contributor, and attack that particular block or a transistor, and maybe do this is called node scaling. So maybe node scale that particular block and leave the rest as is, right? So that is one way of going about designing. So this is while we want to keep the architecture same. Now, obviously, when you get sometimes this is also not sufficient, then you'll have to find out innovative architectures to reduce noise, and that's what the researchers are mostly inclined to do, right? So if something is not working, even after doing all these things, then you try to figure out what other configurations you have. So at that time, the research goes into finding out the nitty-gritty of that circuit topology. Need not necessarily be on a network level. Okay. Okay. So now let's so in the assignment, by the way, all of you got the assignment, right? Okay. So in the assignment, you must have seen there are some noise analysis questions, and there are some control sources in the analysis also, right? So now, why don't you tell me how do I go about solving a generic LTI network which has control sources plus noise sources? I want to find out the total output noise. What should I do? So let's say I have one resistor here, maybe one voltage controlled current source here. Let's say call this Vx. And I want to find out the noise from here. So how should I go about evaluating this?
What's the noise means?
Right. So standard thing to do is find out the transfer function from here to here. If I have a noise source here, maybe the transfer function from here to there individually, and add them up in power. Correct? That is the most standard thing to do. That is what I also do. But now, can you connect this to interreciprocity? Because this is like if I have 5 different noise sources, I have 5 different transfer functions. Evaluating 5 transfer functions is not, I would say, time efficient, right? So can you connect this to interreciprocity? Correct. Okay, so let's take that. So what he's pointing out is ultimately I am interested in what, let's say I call this as a VN1, correct? And I call this, let's say, the noise associated with this is VN2, correct? By the way, when I say that I'm interested in the noise voltage at the output, it's not necessary that you have to find out the noise voltage only. Okay, let me rephrase. So let's say so I'm taking a step back, okay? So let's say I have a network. You have found out the noise voltage. I don't know how, but you have found out, okay? Can you relate it to noise current? If in order to find out the noise voltage, I'll open the port and look at the voltage that has accrued, right? Let's say I want to find out the short circuit noise current. How does this VNO and INO, how are they related, or are they, right? So they're related with the Thevenin's impedance, right? So you know that your VNO will be, so in this case, since we're talking about power, So your sigma squared Vn will be RTH squared times sigma squared of INO. Right? So in principle, you can find either the short circuit current or the open circuit voltage, whichever is convenient. Right? Now choice is yours, right? Whichever is convenient. Now in general, at times you will see that, especially in analog circuits, finding out a short circuit current is often more convenient. The moment you short something, many of the other things go off, right? So, I mean, obviously that's not a generic statement. It depends upon if something is connected in shunt or series, right? So if something is connected in shunt and you short it, then it helps. But in general, you will see what there is another usefulness of short circuit, because that hopefully will get clearer as time progresses. So let's say now I go back to the analysis. So I have this, and let's say I have this, and maybe there is another resistor connected here. This is VN1, this is VN2. And let's say I am interested in finding out the short circuit noise current. Okay. So now if I want to use, reciprocity, okay, before using reciprocity, what am I mostly interested in? I'm interested in the transfer function from Vn1 to In, correct? So we want, let me call this H1, and I'm interested in this transfer function also from Vn2 to In. I call this H2, right? So how do I find out H1 and H2? I simply keep each of these noise sources individually and assume maybe there is a voltage excitation in place of the noise source, and do our usual transfer function analysis to find out whatever is In with respect to that. Now, we established the fact that this is a cumbersome activity if we have multiple of these noise sources. So we would like to use reciprocity, right? So now, if I want to use reciprocity, so now tell me what would you like to do? Let's consider only one of these noise sources for the time being. So this is as is. So what would you like to do? So this port remains port.
Voltage and
Okay, so can you elaborate on that?
like we did not for the sources means memory part.
Right.
Or we taken out and we did
Okay, fine. So I agree. So let's say what he's saying is, this is my noise voltage was here, right? So I take out this as a port. Fine. Then so if it helps, then I also take this out for analysis purposes. Vn1. So I want from Vn1 to In in a reciprocity format. So what should I do? I'll flip the control source, but what about the application of? No, what I meant is that application of the excitation and observation.
voltage source at
Correct, right? So I'll apply a test voltage source here. Correct. So I'll apply a test voltage source here. So this was kind of the hatted network thing, right? So if I still call this V2 hat, right, or Vn hat in this case, what should I be interested in? Current, right? So I should be shorting this. And the current through this will be, if everything is correct, this current will be H1 times Vn hat. Okay, I'll do. So still not accurate, because I said if everything is correct, everything is not correct. So what I need to change? The control source terminals also have to flip, correct? So the control source, this is a voltage control current source. So this becomes, so if this is 1 dash, so this remains 1 dash, this is 2 dash. So this remains as is. So this becomes, the control source itself changes port. And if this was GM times V11 dash, so this becomes GM times V22 dash. Okay. Now tell me what's going to happen. What should I do for H2? H2, that is, the reason I'm doing reciprocity is it is supposed to be easier to evaluate, right? Otherwise, why should I evaluate? Why do I take that extra pain? So I want to find out this H2. So can I find out the H2 from the same test bench in the bottom, or do I have to do another experiment?
For multiple sources,
Right.
not control sources.
Yeah.
Taken out everything.
Correct. So now tell me, what should I do here? You are right. So what should I do? So basically what you are saying, if I understand correctly, is you take this out here. So which means that, so maybe I have to draw it slightly bigger. So whatever was taken out was this. So this has to be shorted. Correct? And this current will be equal to H2 times Vn. Correct? So now, basically now I am evaluating this interreciprocal network by applying a voltage source Vn at port 2 and reading of the short circuit currents across wherever the noise voltage sources were supposed to be present, right? And if you are doing a simulation, then even the better thing to do is to ensure that this Vn, instead of being a generic Vn, is probably a voltage source of amplitude 1, phase 0. Then the absolute value of the current itself will become H2, and the absolute value of the current itself will become H1. So you basically read out the exact value of the current, and that's what it will be. Yes. Good question. What about the direction? I did not pay attention to the direction of the current at all, but why did I not pay attention? I made an assumption without explicitly talking about it. No.
Adding all the power and currents. And
yeah, right. So
will be converting into power. So
exactly, right. So ultimately, all are uncorrelated, right? Every source is uncorrelated. Direction goes up, direction goes down, doesn't matter. Correct. So that's a good question. The direction of the noise source does not really matter. So if you flip, for example, you take this Vn1 and you flip it on its head and give minus Vn1. The final output power for that, you are anywhere doing Vn square. The variance of Vn1 and minus Vn1 are same. So the direction doesn't matter. But if you have to do now, to complete the thought, if for some reason there are some class of circuits where the direction matters, if that is true, then you will have to ensure that the direction is taken care, right? But yeah, go ahead.
Noise part.
Then you'll have to take care of the direction. Then you have to definitely take care of direction.
We check it,
No. So let's do. In this case only. Now help me out here. So how do I do this noise? So for example, when we did this, recheck, as in all you have to do is assume that this is a normal LTI network, and you are trying to figure out the port relationship, right? So easy thing to do is to say that here, what did I do? Here I had V1. This was shorted. So I was interested in, let's say, I'm using the generic nomenclature, not related to this, right? So this was I2, this is I1, and I am exciting here with V2 hat. I am shorting, and I know that this is I1 hat, right? And this is I2 hat. So what relationship am I looking for? I know that V1 times I1 hat plus V2 is 0, which is 0, should be equal to, first term is again 0, then second term is V2 hat I2. So the relationship is in the everything is positive if the direction is kept as is, correct? So in this case, the direction should be inside, correct? So if I keep it like this, and if I assume this is also like this, similarly here the direction will be this, right? So if it's not a noise, then definitely direction matters, right? Yes. Sometimes in case of noise also direction matters. If there are noise from multiple paths, same noise from multiple paths that get added up, it's possible. So I'll show you an example. Any questions so far?
So
Yes.
can we do one thing that we have a network and at the output we Thévenize it,
Okay.
and then we say that the total power is 4 kT into RT.
Yeah, that's the next thing we are going to see. There in certain cases you can do that. In certain cases you cannot. So that's actually called the Nyquist noise theorem. Okay, we'll see why it comes. But before going there, let me ask you one question. Let's say I have a scenario where let's say I have a current source. And forget current source. Let's say I have a resistor. Okay. And then I have a capacitor divider. Okay. I find out the noise path spectral density across this capacitor. Let me call this C1, C2, C3, C4. So C1 to 4 are all C, so identical. This is R. I'll get some, will I get zero noise voltage or will I get some noise voltage? I'll get some noise voltage, and the source of the noise will be, yeah, it's basically the resistor. So I'm going to get some noise. There will be some resistance. It's a resistance R, and there will be some noise here, and part of that noise will accrue across C2. Correct? Okay. What about if I take from here? So let's say I call this VN2. I call this VN1. Similarly, I will get some noise voltage across VN1. Right? Fine. So now let's say I define a new variable, V0, which is VN1 minus VN2. Okay. So now I am interested in the noise of V0. Okay. So will I get zero noise or will I get some noise? Why some noise?
Because the noise will be zero.
Okay. Mean of the noise is zero everywhere. Fine. So why some noise?
So we get different noise. Different. But NTM power, we have seen power, so it will be zero.
I didn't. So if you see power, then VN2 should also be zero if I do that argument, right? I didn't understand that argument. What do you mean by at the end we are seeing power? Okay, think about it. I'll come to your question. You said that ultimately their variance are going to add up. Is that what you mean? VN1, the variance of VN1 and variance of VN2 are going to add up, and I'm going to get a non-zero number. Any other thoughts?
The noise produced by the same source, so I don't think they're uncorrelated.
Exactly, right? These are not uncorrelated. So the stuff that is causing the noise on VN1, right, is the same that is causing the noise from VN2, because ultimately this guy, so now let's assume, now the time domain intuition matters. So let's say you are doing the experiment and you found out that any point of time at any, or rather across time, your noise profile is like this. Okay. So, and you observe across C2, and you are going to get a noise profile which is similar, but depending upon the type of attenuation, you're going to get something, right? So maybe something like this. Across C1, what are you going to get with respect to time? C1, C2, C3, C4 identical. You should get the same thing, right? Because transfer function is identical, input is identical, even though it's a noise, correct? So now if I do this minus this, I'm going to get a flat line. I'm going to get 0, right? Because they are perfectly correlated. So you have to be careful when you are doing a circuit analysis to figure out whether there is some correlation with respect to a noise source, right? It generally happens if you are if I took an explicit case where I'm taking a difference, but it can happen that there is multiple paths for a noise to come to a same node. And if it travels multiple paths with different phase shifts and all, then you can have a problem if you do individual transfer function analysis. So the best thing to do, that's why, is to find out the total transfer function first and then apply the noise correlations and noise relationship, right? What I mean by this is, do not, if, for example, in this case, the variable of interest is V naught directly. So you should find out the transfer function from here to V naught, not from here to Vn1 and here to Vn2. Is that part clear? So if I find out the transfer function from VNR, so if I say V naught over VNR, what is this? Which means I am exciting something at VNR. Let's say there is a AC voltage source at VNR, and I'm trying to find out, transfer function should be capital, V naught over VNR. So what should I get? This should be easy. 0. Correct. I should get 0. Right? If I get 0, it doesn't matter what VNR is. I'll always get 0 in terms of PSD. Isn't it? But if I find out Vn1 by VNR, I'll get some non-zero value. I'll get some H1, right? Or some H I'll get. Similarly, which will be exactly equal to Vn2 by VNR. And I find out, and I find out the PSD by saying it is H squared times 4kTr for Vn1, sigma n1, or rather SVN1 is this, which is also equal to SVN2. And then say that these two are subtraction of two variables, their variances add up, and hence SV naught is equal to 2 times H squared 4kTr. So that will be incorrect, right? So the point that I'm trying to make is whenever in doubt, find out the total transfer function from the source to whatever is your desired output means. Right? If it's given that this is that voltage, fine, find out that voltage. If it says that difference of the voltage, then find out the transfer function with the difference voltage to that. Right? So don't fall into that thing that I will find out this individually, that individually, and add up. That always doesn't work out. Yes. Yes.
Noise cancelling.
Hmm.
So whatever noise that is being cancelled, there are two things. It is cancelling in time domain.
Hmm.
As well, it is cancelling in frequency domain as well because of being correlated to each other.
Yeah, if it cancels the time domain, naturally all its transforms will also get cancelled. Yeah. Okay, fine. By the way, I mean, this is an useless circuit, right? Because it's no signal also. And there will be nothing from VN2, even if you have a voltage source there, I mean, signal source there. But this is just to make a point. Okay, so now let's go to that Nyquist noise theorem thing. It's a very interesting theorem. So it's, but it has some limitations, but it's very useful nevertheless. So let's say I take one network which has only RLCs, no control sources, right? An important distinction, no control sources, only RLCs. So, okay. So let's say I have 1 R here, 1 R here, capacitor, conductor, whatever. Like before, I would like to find out the noise power spectral density. Let's say I'm interested in finding out the voltage noise. Okay. So like before, what can I do? I know that. So now what I'm going to do, I'm going to model everything as a parallel. I can also model as a voltage source, but let's model it as a parallel current source, noise current source. Okay. And I'm now interested in finding out Vn naught. So for that, I again, like before, I have to find out the relationship between In1 to Vn naught, In2 to Vn naught, and so on. Correct? And this is R1, R2. So if I do this, what am I going to get? I'm going to get, let's say this relationship is H1, this is H2, and so on. So I will get SVN naught should be equal to 4 KT. So with rest, if I am doing only for first one, I'm going to get 4 KT over R1 times H1 squared. Correct? Similarly, 4 KT over R2 times H2 squared, and so on. Correct? So why 4 KT over R1? Current, right? Good. So essentially, what I'm saying is I'm doing 4 KT summation of VHN squared over Rn, summed over all n. This is what we are doing. Okay. So now let's use reciprocity, just like before. Okay. So for same network, I'm showing for only one resistor. Others are also present. So here I was having current and I was observing voltage. Now, if I want to do reciprocity, what should I, in second port, what am I going to club? Current, okay. I'm going to put a current source, right? So let's say I2 hat. And I'm going to observe the voltage across. I'm not taking it explicitly out, but you can assume it is taken out. So I'm going to observe this voltage, let's say V1. Okay. Similarly, I'm going to have something here. I'm going to observe this voltage V2. Maybe this is becoming difficult to keep track of the notations. I'll just call this IN then. Okay. So what do I know? I know that the relationship between V1 over IN is equal to H1. Correct? IN hat rather is equal to H1, right? So I know that H1, or if I don't have to bother about the sign, I can simply say that mod H1 is equal to mod of V1 by IN hat. Right? Okay. So basically, this is true for, let me call this I0 because N I have used there also. Okay. Okay. Fine. So now let's think about what is the power consumed in the network. Right? It's a leap, but let's amuse me. Just tell me that what is the power consumed in this network? How am I going to find out what is the power dissipated inside the network? Total power should be 0, including I naught, right? Yeah, true. But let's say I have to do part by part analysis. What should I do to find out power dissipation? I have to add up all the power consumed by the dissipative elements in the network. Correct? And the dissipative elements are only resistors. Correct? So I can say that power dissipation is equal to V1 squared over R1 plus V2 squared over R2 plus so on. Correct? So this is basically summation of Vn squared over Rn. Okay? Fine. So Can I also say that power dissipation in the network is also equal to the I square, whatever is the current that is flowing in, times the real part of the impedance that we see? Right? So if I find out this impedance Z of j omega, can I say that power dissipation is equal to naught squared times real part of Z of j omega? I can say that, right? Yeah, I mean, we are talking about average power dissipated, active power only, right? Yeah, true. So now these, which means these two are identical, right? Okay. So this is, which means that this is equal to summation of Vn squared over Rn. Now the fun part is, if I naught is equal to 1 angle 0, right? So if I naught is equal to 1 angle 0, then your power dissipation is equal to real part of Z j omega, which is still equal to Vn squared over Rn. But what is Vn squared? If now let's concentrate on this expression. If I naught equal to 1, then Vn is equal to Hn. Correct? So I can basically say that this is equal to summation of mod of Hn squared over Rn. Correct? So now the next step is simple. Multiply both sides by 4 kt. So this side I take this side. So basically 4 kt times summation of mod of Hn squared by Rn is equal to 4 kt times the real of Z of j omega. Correct? So what is this? It is the total power spectral density observed across the output port of my network, right? So this is the SV and O. Correct? So this is basically telling you this is equal to, you do not have to do all the reciprocity and all also. All you have to do is find out the input impedance Z of j omega and then extract its real part. 4 kt times the real part is the power spectral density. Right? Make sense? So this is what you call Nyquist noise theorem, and it has, I mean, it makes life extremely simple if you have only RLCs. For example, if somebody gives you, let's say I give you a network which has a bunch of resistors. And ask you to find out the noise spectral density here. What will be the noise? You have option to say that I am going to put a noise source everywhere and then find out, or you do reciprocity and everything. But alternatively, you can simply say that I'll find out the input impedance. It's a ladder network. I know it will parallel series. I'll come up with a number. 4 kt times that number is your power spectral density. Right? So that becomes really simple. But the thing that you have to remember is that this is only true if you have RLC inside. If you have control sources, this is not true. Why? Which part of this analysis is not valid if you have control sources? Yeah, right. So the power dissipated, I cannot really say it equal to this, because if you have control source, that is also, that does not necessarily dissipate power, right? That gives you, that generates power also, and hence this relationship is not valid. So if you have control source, that relationship is not valid, and hence you cannot use Nyquist noise theorem for control sources, but you can use it for if you have RLCs. Okay. I mean, you can do one dummy example, the same RC network. So we found out by finding transfer function what is the power spectral density here, right? So you can find out this way also now. So what is What is Z? Z is basically R times 1 by j omega C by R plus 1 by j omega C, which is, right? So its real part is basically R by 1 plus omega square R square C square. 4 kT times R is your fast spectral density, right?
If we add one more RC,
You can add whatever you want anywhere. I did not, in this expression, there was no assumptions as long as we have RLC. Right? So you can have everything. So in the assignment that I have shared, you will see that there are multiple combinations of RLCs. You can do it and also verify. Okay, any questions so far? By the way, this is this type of giving this type of networks, some sort of resistor divider ladder and all, and asking to find out noise is a very good interview question. If you go for analog circuit interviews and in a slightly higher position, they are going to ask this almost invariably.
only thing that we have to do is just need to figure out the
Impedance. Yes.
let's say you have multiple independent sources. So current circuits will open.
Same. Everything that you know about finding out impedances will apply. Yes. Because if when in doubt, go back and see the proof, right? If you have independent sources, which part of the proof is not valid? For noise, they are anyway nulling them, right? Okay, fine. So we have made some significant progress in terms of doing analysis of noise. Now we'll do further analysis, but now it will be a slightly different type of analysis. So very often, till now what we have been doing is we say that we have a network. Yeah, I'm looking at this output. Output is going to have some noise voltage or noise current. I'm interested in the power spectral density of that thing. Now, very often you are going to have one block driving another block, and subsequently it will cascade one after another. And it's not necessary that you are in charge of designing each of these blocks, right? Somebody else is designing something, somebody else is designing something, and so on. So normally when you do signal analysis, forget about noise. When you do signal analysis, let's say I am designing this. I am designing this block. This is block 1 I am designing, and block 2 somebody else has designed. It's already designed. So what information would I seek from the designer of block 2 to ensure that this block 1, I design block 1 efficiently? Forget noise, normal signal analysis. Pardon? Yeah, impedance, definitely, right? If nothing else, I would like to know what am I loading? What am I driving? Am I loading a resistive load? Is it a very small resistive load? Is it a large resistive load? Am I driving an open circuit capacitor? That at least I need to know that. So I need to know the input impedance of this. Similarly, if something is driving me, so I need to find out this output impedance of the previous block, right? This is the bare minimum I need, right? But the reason I am harping on this is because this input impedance does not capture everything about the block V2. It only captures that relevant information that is relevant to me for driving my block, or for driving my system or designing my system. Similarly, when I do noise analysis, B2 might have n number of noise sources, but I need to encapsulate that information into one particular number. Just like I have Rin, which is one particular number, I need to encapsulate that information into one particular number so as for me to decide how much noise, what's the noise for which I should design B1 for, right? So the reason being, so I'll tell you the reason, then probably it will be more appropriate. So let's say this is an amplifier. Let's say this is an amplifier of gain A1, and input impedance assumed to be infinite for the time being. Okay, let's say Rin is equal to infinite. And this is driving another amplifier, A2, again Rin equal to infinite. Now, if I know this amplifier is noisy, this A1 is, let's say, is noisy, then just like we could isolate a noise, for the purpose of analysis, we could isolate a noisy resistor into a noiseless resistor and a voltage source in series. I can do the same thing for this particular block also. Nobody is stopping me from doing that. So this is, I am saying this is noisy. So if I can forget about this one for the time being. So this, I can basically say this is equal to a noiseless amplifier and maybe a noisy voltage source, ENA, and then connected to A2, which also has a noisy voltage source, and so on. I can say that, right? Block diagrammatically wise, there is nothing wrong in it, right? Loading and all things are different things we have to bother, but at least in the block diagrammatic representation, this is fine. So now let's assume that this block is already designed. Somebody has designed this block, you'd have no control over it. And let's say VN2 has some power spectral density. Let's say SVNA2 is, let's say I just take a number, let's say 10 into 10 power minus 18 whole square per hertz. Okay. And let's say A2 has a gain of, let's say A2 has a gain of 40 dB, which is 100. Okay. So now, how does this information help us in deciding the noise noise specification of A1? What should I design for? So let's assume that I have burnt like enormous amount of power in A1 to reduce the noise, because that I know I can do. And after doing that, I found that this VN1 is, I don't know, maybe 10 power minus 22 volt square per hertz, right? Let's say after doing a lot of power burning and all, I found this. So what will be the total output noise here? What will be the power spectral density here? Or I should have said SV. So in terms of SVNA and SVNA1 and SVNA2, what will be the power spectral density? SVNA1 then into A2 squared, because it's going through a gain block, right? That is the transfer function, A2 squared plus SVNA2, right? So which means what? In this case, this is 10 power minus 22 into A2 is 10 power 4. A2 squared will be 10 power 4 plus 10 power minus 17, correct? So this is 10 power minus 18 and this is 10 power minus 17. So still at the output, I am dominated by the noise due to A2, correct? So this is much less than the noise due to A2, correct? So would you then rather agree that I have probably over-designed A1 for noise? Which means that I do not need to reduce the noise of A1 to the level of 10 power minus 22. You agree? So which means that I can probably reduce, I can burn 10x lower power and get it down to 10 power minus 21, let's say, or get it up to 10 power minus 21. If I can do that, then this similar number will be 10 power minus 17 plus 10 power minus 17. So now it's comparable, equal. Yes.
Not the problem. Earlier case was good, right?
Oh, yeah, definitely it was good. But earlier, let's say if I reduce the power by, if I reduce the noise by 10x, which means that I can reduce the power also by 10x, right? I can go to P by 10, right? So, okay, P by 10 is probably I did an overkill. Let's say I go to P by 5. So this goes to twice times 10 power minus 21. Yeah, right? Yeah. So this becomes how much?
Contribution even when over designing at the output from A1.
Okay, so think of in this way. I am going from 10% contribution to maybe 20% or 30% contribution. How much power am I reducing? I am reducing, I can potentially reduce 3x or 4x amount of power at the system level, isn't it? So the point that I'm trying to make here is, unless you have the information of the noise of this block, you do not have the information of, or you cannot start designing the previous block for noise. Right? You might end up designing something which is highly over designed, or you might end up making something which is really noisy. Right? For example, if I say that if I go the other way around and I say that this SVNA is NA1 has the same power spectral density as the second block, which is equal to, how much did I assume? 10 power minus 17. Right? Let's assume I have used the same block instead of 8. I have basically repeated A2. So then, can you comment on the power spectral density on the output side? Right? So it will dominate. You are going to get 100 times SVN1 plus 1 times SVN1 effectively. Correct? So then it's like a really bad design in terms of noise, isn't it? So the point that I'm trying to make here is, you need certain information about the succeeding block to design for noise of the preceding block. So you want, just like you wanted input impedance for designing for signal, so you need one particular encapsulated number associated with the noise of this block, and that number is the total noise. Okay, not necessarily, I don't need the gory details of what goes in making A2. I just need to know one number, and the total is number is the total noise. Now this total noise is at the output. So if I just say total noise, that will also not be sufficient. I have to tell what is the gain also, because the noise of the preceding block is going to get gained up and then come to the output. Correct? So which means that if I have to say the noise, it's not only sufficient to say noise, it's not a single number I can specify still. I still have to specify gain and noise. So if I have to then get it down to a single number, can you give me a better solution? Yeah, I can basically say that. How are we modeling the noise? We are modeling the noise like this. This is, let's say, A, and this is SVN. Let's say I call this SVN. So now this addition block does not really exist, right? This is, I made it up just to encapsulate the effect of noise. Now I need not necessarily put this addition adder at the output of A. I can put it at the input of A also. The number will be different, but I can put the adder at the input of A. Right? So I can as well put it here. This is the problem. So what will this be so that the output SV and not remains the same? What should this be? It should be SVN by A squared, right? So that this output power spectral density is SVN naught. So this part is called input referred noise. And it encapsulates the effect of gain also into your noise specification. So many times you are going to see data sheets where they will refer to as input referred noise is so much. So when they mean that, they essentially mean this, right? When they talk about that. Any questions so far? So now I have made certain assumptions here, and the assumptions that I have made is your input impedance is infinite, or ideal sources and all, right? Then this model is accurate. But what if your input impedance of a network is not, okay, instead of going to the input impedance, let me ask you this. Is it, so this is, I can also express as some VNA and A, correct? So is it necessary for me to express this emulated noise source, which is not a physical noise source? It's not like you are going to connect a voltmeter at the input of of the amplifier and you are going to get a number. You're never going to get that. On the other hand, if you connect a voltmeter at the output, you are going to get a number, right? So output referred noise has a physical significance. Input referred noise does not have any physical significance. It's totally a math model. Okay. So my question is it necessary for me to model it like a voltage source? I can also model it as a current source. If I'm modeling, I can model it as a current source also, right? But under what condition do you think the modeling of a voltage source will be more accurate than a modeling of a current source? No, okay, not necessary. Okay, let me make the question clear. So clearer. So let's say I have one block that is driving this amplifier A, and I'm saying that I'm going to model it as a voltage source. Okay. So what should I do with this terminal? What should I do with this terminal? This is the output of the previous block. These grounds are connected, let's say. So what should I do with this terminal? These two. Should I connect them like this? What should I do? I can connect them. Okay, I'll connect them. Now assume that your input here, where should I put it? So let's say this has an output resistance, right? This previous block has an output resistance. Let's say this R naught equal to 0. Right? Can happen, very low, 0. And let's say this block is also, it maybe has an input impedance where Rin is also equal to 0. Right? So now what am I seeing? In the math model, what am I seeing? So Rin is 0 means this is like this, right? So I have a resistance like this. This is what is happening. Correct? So this, you might say this is a problem which probably is not a physical thing, right? So let's not bother about this problem having short circuit, because we can always say there is some resistance, right? But let's take a realistic thing, right? So let's say this R out here tends to infinity. It's an open circuit. Very easier to visualize an open circuit. At low frequency, at least you can have very close open circuit, right? So let's say it's an open circuit, which means what? You have this, correct? Now note that this amplifier A is noiseless, because I have, in the model, I have assumed that all the noise has been taken out and it has been added to this Vn, correct? So now in this model, right, when these two blocks are cascaded and I want to find out the noise due to A, in this model, what am I going to get? What? 0, right? Does that make sense? I said that let's say there is a case in which Rin equal to 0. If you do not want to make Rin equal to 0, that is also fine. Let's say there is a finite Rin. Let's say there is a finite Rin. Let's say this finite. No problem. Let's do it finite Rin. So what is Vn naught? What is the voltage across Rin? 0, right? There is no current in the loop. So voltage across Rin will be 0. So Vn naught is 0. Correct? So then is it an accurate model? Is this an accurate model? Shouldn't, right? Because if a model is accurate, I should be able to get steady output, whatever be the input, however I connect the input to be. Isn't it? One might say, okay, applying an input might influence the output because there can be some loading effect between input and output, all those things, but let's not consider those things. But in general, just because I open circuited this side, my output voltage in this model goes to 0. So clearly there is something wrong with the model, because in the device, I'm never going to get 0 because I just open circuited the input. Make sense? So what? So similarly, I mean, you can make a, so okay, before going similarly. So now can you tell me what can I do to ensure that this Vn naught doesn't give 0? Model has to have a current source. Correct? So in this particular case, if I simply have a model which is input referred current, not voltage, then that would suffice. Because your input, whether even if it's open, this current source will flow in, create a voltage, and then that times A will be your Vn naught, right? So your SVN naught, if this is I in, will be SI in times R in squared, which means your SI in, which is the power spectral density of the noise source, will be the observed power spectral density of the output divided by R in squared. Right? Make sense? So clearly, I took an extreme case. I opened it and showed you one. I can similarly short it also and show you another case. So, but if I have to make it a generic case, what should the input referred model be? It should have both. It should have both the voltage source and a current source. So the most generic input referred model of any input referred noise model is this. This is a 2-port. Maybe you have an R in or Z in, and this is your port 2. Okay. So ideally, if somebody has to tell you what is my input referred noise model, one has to tell you this entire thing. Correct? But in most analog circuit applications, you are going to see that knowing one of them is sufficient, because in most, let's say you're doing instrumentation amplifier or something like that, in those most cases, Rin tends to infinity. Right? If Rin tends to infinity and the input impedance of the previous block is, the output impedance of the previous block is much smaller than whatever impedance that you are driving, what I'm saying is essentially, if you have a scenario in which this R out tends to 0, so then this goes to ground, then this goes here, this is IN, and this kind of tends to infinity, right? So this tends to 0 and this tends to infinity. If that is the case, this model is telling you this current noise will go into the short circuit and it will not have any impact. It will not create any voltage. Then you can get away with only a noise voltage source. Right? So that's why in most instrumentation amplifier or low frequency applications, when you see data sheet, they only mention input referred noise voltage, not necessarily noise current. But if you increase frequency, if you go to RF applications, then they have to specify both ideally. Okay. The other part that is of importance is to understand the fact that what is the origin of this Vn and In? This is origin is, by the way, before going to the origin, so let's say I ask you to find out the values of Vn and In. I give you a network and I ask you to find out, tell me what will be Vn and what will be In. What are you going to do? So you have a network. Some network is there which has bunch of resistors and everything, capacitors and everything is there. and these are noisy. I want you to model this as this is noisy. I know that I can model this like the same network which is noiseless, but all the noise has been transferred to the input. I want you to find out the values of Vn and In. So what are you going to do?
Check output noise and accordingly.
Okay, first thing, good, we check output noise, right? Is there a particular configuration you are going to check the output noise? That reciprocity is a method to find out, right? So it can be used anywhere. Think of it this way, right? Let's say this is my block. Okay, I have control over these terminals. And I want to find out the information of Vn and In. And note that I know this, right? So I know the transfer function from this to there and that to there, I know. Because, I mean, that is that is normal circuit analysis. From port to port, I know. So then how will you set it up so that I isolate Vn or I isolate In and find out the total noise? Exactly, right? I can either short or open the input port. So let's say I use it in this exactly the same configuration that I have. And let's assume there is an input resistance, right? Let's assume there's an input resistance. In this configuration, the output noise, CNO, under the condition is input is open, will be In squared, or rather SIN squared, times Rin, SIN times Rin squared, times the voltage transfer function between port 1 to port 2, right? H1 squared. Correct? So I know this. Correct? So I know this, from there I get this. Okay. Now if I have to find out Vn, how should I set it up? I short the input, right? So if I short the input, then this naturally becomes so this In does not contribute to any noise. The entire Vn appears here. This is minus Vn, the way I have drawn. So your SVNO when input equal to open is, sorry, short. Thank you. Is SVN, I don't know what I called it. I simply call it SVN, I think, right? Let's say SVN times that H1 to 2 squared. The H1 to 2 is between port here to there, right? And you know this, so from there you know this. So you do two experiments. You set it up in a short and open circuit configuration, and then you find this out. So naturally from this also you can see that your SIN is SVNO under open circuit configuration divided by Rin squared times mod of H1 whole squared. So if Rin is very high, then SIN naturally becomes irrelevant, right? So it's all a game of what is the input impedance. If the input impedance is of your network is really high, then you mostly you can ignore SIN, but if it's not, then you cannot. Okay.
Is this how we do tape out?
What is that to do with tape out? Now, this is while you are trying to figure out when you, let's say you want to design for noise for any block, you need to know the noise information of the subsequent block, and this information becomes necessary, right? Sometimes in most practical scenarios, often you will find that this SVN and SIN, in most practical cases, one of them will dominate. So you just then, for the back of the hand calculation, you ignore one and just use the dominant one and do. Either you take the SIN, if SIN is dominant, if SVN is the dominant, you take the SVN and do the analysis. More or less, you are going to get ballpark similar ballpark right numbers. Not always, very rarely, both of them are simultaneously used. But in those cases where you cannot ignore either of them, then you have to be very careful, because can you comment on if SVN and SIN are uncorrelated or correlated with each other? Why do you say it's uncorrelated?
Function of.
But the current source and voltage is my model, right? They are not physically present, these current sources.
Also, like, at one time shorting and walking.
Right.
Let's say there is a resistance between opening and short circuit. So both the voltage and the current source will be significant in that case.
If that's the case, so be it. In that case, you will have bigger problem in driving a signal.
Both of the processes, when we are accounting for the contribution from the one source, we are not accounting the contribution due to the other.
No, that is fine. What you are saying is that when I am finding out Vn and In, I am nulling I'm setting up the circuit so that one of them goes to 0. That does not necessarily mean they are correlated or uncorrelated. That's a different question. My question is, physically, are these SVN and SIN are correlated? So let me give you a hint. What is the source of these noises, these input-driven noises? Why do they exist? Because they have resistors inside the block, right? Not Rin, not necessarily. Rin is a model resistance, right? It can be anything inside, right? You have resistors inside. They contribute to SVN and SIN. The same set of resistors are contributing to SVN and SIN, right? Isn't it? So I am only modeling it in such a way that I short input and open input, but it's the same set of resistors that are giving rise to these input referred noise SV and SIN, which naturally means that they are correlated. They have to be correlated, right? So when you do a noise analysis using this, where you cannot really make a just call that whether you can ignore one and you have to use both, then be very careful that you do not do individual noise analysis and then square and add. You'll get a wrong number. Okay, so you have to do a simultaneous analysis with SVN and SIN with the directions of the currents in place, currents and the voltages in place. And then because if it's correlated, then obviously their directions matter. Just the example that we saw here. The trivial example, but still. Here, if I say the directions don't matter, which means I can say the voltage here goes up, voltage here goes down, difference amplifies, right? That's not true. Directions matter. So when things are correlated, directions of matter. So you have to do you have to do appropriate analysis taking directions into account. Okay. Okay, fine. We're out of time. Let's stop here.